Hi everybody, welcome to another video in trigonometry, section 6.2. In the next two sections, we'll study about trigonometry equation. This is the first part. Right. So trigonometry equation is an equation that contains some trigonometric function, and the variable, of course, belongs to that trigonometric function. So pretty much what we have is something like this, where we're trying to solve for x inside a trig function that satisfies some condition. Right. So to solve for this, sine x equal to square root of 2 over 2. So let's take a look at a circle, a unit circle, that is. Sine of an angle is equal to the x, is equal to the y values. So when we have the y values is equal to square root of 2 over 2. That y values, there will be 2, 1 over here, and 1 over there. These 2 points have the same y values of square root of 2 over 2. So the sine will be equal to those 2 values. If it is in a unit circle, of course we can go around and around that. So at first let's just write the solution. So if sine x equal to this, by the way, previous section we learned about inverse function. We might use that, but this is not going to be the only answer we have. Keep in mind. So, of course, you can look at the unit circle, or you can use. If you use a calculator, that's not the only answer we have. So we have to kind of draw the unit circle and see where actually on the unit circle we'll have the solution. Right. If we use a calculator for the inverse function, make sure that is in the degree mode. So in that case, when we do the sine inverse of square root of 2 over 2, yeah, that should be 45 degrees. And then of course 45 degrees we can convert to radian. The answer, it says here, write the answer in degrees and radian. So first, if sine x is equal to that, we can say x is equal to sine inverse of square root of 2 over 2. Right? And of course that turned out to be 45 degrees. But of course that's not the only answer we have, right? If we have this point 45 degrees, it's at this point. Now we can also go around more revolution, or we can go backward. So the key here is when we have the answer like that, we have to plus 2. Now if it is in degree, it's going to be plus 2 k pi, or let's use 2 n pi, because 2 pi is a revolution. So whenever we have a point here, if we go an extra revolution of 2 pi, we get back to the same point. So plus 2 n pi here will give us all the coterminal angles to 45 degrees. Of course, if it is in degree, we're going to use plus n times 360 degrees. So n times 2 pi give us a number of revolution. A revolution is 2 pi and or 360 degrees. So let me just write this. One revolution is equal to 360 degrees, or equal to 2 pi radian. So that's why we add 2 n pi here, so we can go extra revolution, and n here can be any integers. So if we have n equal to 1, we go 1 extra revolution, n equal to 2, 2 extra revolution, and so on. So in general, it's going to be in that form. course, or if we write in radian, we can say 45 degrees will be pi over 2, pi over 4. And then of course, instead of plus n times 360, we get plus 2n pi. So if it is in radian, we're going to plus 2n pi. If it is in degrees, plus n times 360. That is for sine and cosine, because that gives us coterminal angle. Right, so that gives us on the position, the solution there. Now, how about this point over here? If we want to get this point, notice, let me just zoom out so you can see that better. Now, if we have here is an angle, say 45 degrees in this case, then this is also 45 degrees. And if we want this angle 180 degrees is half a revolution, we take out 45 degrees here. So that gives us 180 minus 45 degrees. So this is one way to write the answer, or we can also have pi minus, or 180 degrees minus sine inverse square root of 2 over 2. And then as always for sine or cosine, we can plus 2n pi. Okay. Now if we write this in degree, of course we'll write 180 degree minus 45 degree. That is the sine inverse. Plus 2n pi in degrees will be n times 360. That gives us 135 degree plus n times 360. Or if we want to write in radian, sorry, not one. If we want to write in radian, 135 degrees is 3 pi over 4 plus 2n pi. Right. Don't worry about this. I just want to write this, and then after that we have some certain formulas, and we can just work with that. So the key here is two things. For sine, the solution might have to add 2n pi or n times 360 degrees. If it is in radian, 2n pi. If it is in degrees, n times 360 degrees. That's the first thing. Second, cosine, we will have two values, one over here and one over there. By that I mean the solution. One of them is the sine inverse. The other one is the pi subtracted, or 180 subtracted. Or in general, we call this the supplement to this. These two angles are supplement to each other. Right, so that is sine. Now let's look at the equation involving cosine. Now we wrote a unit circle. Cosine of an angle is the x values. The x values in this case is negative square root of 3 over 2. Let's see about that. These 2 points will have the same x values. So if we want to solve for theta, first thing we do is cosine inverse. And then either we plus n to n pi or n times 360 degrees, either way. Usually I will write to n pi because by default it should be in radian. Now, but if we use the calculator, cosine inverse, of negative square root of 3 over 2. Of course, if we don't have that, we can always use the unit circle for find values. So that's 150 degrees. And then if it is in degree, I will use n times 360 degree. So I get coterminal angles can go around and around. As long as I have the same point, that's correct. And 150 degree, if we write in radian, it's going to be just one time. If we want to change this to radian, put 180 at the bottom and pi on the top. Cancel the degrees. 150 over 180 divided by the 30. We have 5 pi over 6. And if it is in radian, or in that 5 pi over 6 form, it's going to be 2n pi. Right. So that is all the solution at this point. Now, we also have the solution over here. Those 2 points have the same x values of that. So in that case, if this is positive angle, like 150, we just need to go opposite direction and get to negative 150. So theta will be equal to negative, I should emphasize this, because those 2 points have the same x values, the positive or negative angle. Cosine is an even function, so that's why they should be the same x values if the values are opposites. So do that, and then plus 2n pi in general. And negative, we already did the inverse, that's 150 degree, because plus 2n pi. Or in radian, negative 5 pi over 6 plus 2n pi. Sorry, if it is in degree, that will be n times 360 degree. Right. So for cosine, it is cosine inverse or opposite to that, and it's always plus 2n pi or n times 360 degree to get all the coterminal angles. Now for tangent, I did mention that we have the tangent axis is the one that is tangent to the unit circle. At the point 1, 0. So now if we want square root of 3, square root of 3 is like 1.7 something. So that is square root of 3 on the tangent axis. If we connect that back to the unit circle, from that point connect to the center, there will be 2 points. And these 2 points will have the same tangent values of square root of 3. So first, we're going to write that as the tangent inverse. And potentially we might have, it's not 2n pi anymore. For tangent, it's going to be a pi to go to the opposite point and then get back to that plus a pi. So in that case, would be just n pi. So, yeah, just have a revolution. And in tangent, actually, that's all we have. Tangent inverse of square root of 3 that's 60 degrees plus n pi. Because if it is in degrees, that will be pi is equivalent to 180 degrees. Now, or if we want to write this in radian, 60 degrees pi over 3 plus n pi. Because in tangent, we can just go one revolution, half a revolution to get to the opposite side, and then half a revolution to get back to that point. Right, so now one more thing about the 2n pi. Remember, we did study that in section in chapter 4. A period for sine and cosine by default for sine x and cosine x are 2 pi, or one revolution, or 360 degree. So a period of sine cosine are 2 pi. A period of tangent and cotangent are just a pi. Right? So tangent, the period is a pi, so that's why we just add n times the number of period to it. Sine cosine, the period is 2 pi, so we add n times 2 pi to it. Usually you can also write n times 2 pi, but usually we write the number first and the letter later. So that's why I write 2n pi. Once again, the period of sine cosine are 2 pi. A period of tangent is a pi. And tangent, that's all we do. We don't have anything on this side. Right, now those just a sample. Now, a more systematic way to do this. By the way, if you read the textbook or different textbook or get that somewhere, they might do this differently. The way I do this is the most systematic way to do this trigonometric function. So, and I think that is easy to do. Right, so first, if we have sine of something equal to something, then to get back to the angle, we just do the inverse, sine inverse. Same thing if we have cosine, it can be cosine inverse. If it is tangent, it will be tangent inverse, right? So when we have trig function equal to something, the first solution is just second inverse. Now, the period for sine and cosine, the period is 2 pi. And for tangent, the period is just a pi. So we add 2n pi here, and once again, n will be all any integers. And by integers, I mean the z. Let's start from -2, -1, 0, 1, 2. Those numbers. It can be any of those. Alright, so that's the first part of the solution. Is we're going to take the inverse. And then we add n times a period, whether sine, cosine, or tangent. We do that. Of course, if it is secant, cosecant, and cotangent, we do that differently. We convert to this three function first. Right. Next. For sine, they have the point that are supplement to it. So for sine, we also have this solution. Pi minus that, or 180 minus that, or we call supplement. To the sine inverse. So sine, we have the sine inverse and its supplement. For cosine, we have the cosine inverse, and then with the minus here, of course, with the minus that is opposite. Some other books write the solution like this, but I don't want to write like that. So sine, we have the sine inverse and the complement the supplement. Cosine will have the cosine inverse and the opposite. For tangent, there's nothing. So I write like this. For sine, there is a supplement along with the inverse. For cosine, there is the opposite along with the inverse. And for tangent, there's nothing. However, in tangent, the period is just up high. Right. Now, of course, if you want to write pi, you can write 180 in the place of a pi. Right. So, sine we have supplement, cosine we have opposite, tangent we have nothing, except the period is a pi. And as long as we remember that, then the cosine and sine and tangent we just have the inverse. So that's simple enough. Let's look at this equation. So the first thing we do here, of course, try to get the trig function by itself. So in that case, what I do is -1 on both sides. So I have to get the trig function by itself. And then divide by 2 to get the sine by itself. Now we have the sine equal to something. Then we can use the formula that we just did. The first thing, of course, is the sine inverse. The first part of the solution, we're going to take the angle, in this case x minus pi over 4 equal to, the first one, of course, is the sine inverse, always the trig inverse of that values. Now, here we write the answer in 0 and 2 pi. Don't worry about that. In general, we have to have plus 2n pi. That gives us all the solution. N times a period of 2 pi. That's the first thing. The second part of it, remember, the sine, not only we have the sine inverse, there's always a supplement to it. So sine, we have the inverse and the supplement. And the plus 2n pi just give us a period. Plus n times the period. Right, now let's solve for x first. So we have x minus pi over 4 equal to sine inverse of 1/2. Sine inverse of 1/2 or 0.5 is 30 degrees. 30 degrees convert to radian would be pi over 6. And then we can add pi over 4 on both sides. Pi over 6 plus pi over 4, so 1 over 6 plus 1 over 4 is that. The fraction will be 5 over 12. So we have x equal to 5 pi 5 over 12, and then we will stick the pi to it, plus 2n pi. So that is a solution. Now over here we'll do the same thing. X minus pi over 4 pi, the sine inverse we already did, pi over 6. As always, plus 2n pi here. A period to it. Now we're going to add pi over 4. So we have 1 minus 1 over 6 plus 1 over 4. 1 minus 1 over 6 plus 1 over 4. So 1 minus 1 over 6 plus 1 over 4, so that's 13 over 2. So x equal to 13 pi over 12. And then plus 2n pi. So in general, that's what we have, right? Remember, we have to plus n times a period of the problem. A period, in this case, is 2 pi. So that's why we have n times 2 pi. Right. Now in this problem, we have to pay attention that the answer must be in term of in between 0 and 2 pi. So in 0 and 2 pi, in that case we have to choose some values for n. Now if we choose n equal to 0, then we have x. Over here if we say n equal to 0, then we have x equal to 5 pi over 12. And is 5 pi over 12 between 0 and 2 pi? And 5 divided by 12. Yes, this number is between 0 and 2. So 5 pi over 12 is between 0 and 2 pi. So when n equal to 0, that number is in between 0 and 2 pi. So yes, so this is a solution. And over here, if we choose n equal to 0, we have an angle of 13 pi over 2. And again, 13 pi over 2 is 1 point something times pi, which is between 0 and 2 pi. So that also between 0 and 2 pi. And if it is between 0 and 2 pi here, and we have sine, the period is also 2 pi, then in that case there's only one value of n that make this equation works. So once you find the values, that's good enough. So we have the values of x equal to 5 pi over 12, or we have 13 pi over 12. Right, so sine inverse or the supplement. Sine, we have the supplement. And if the answer between 0 and 2 pi, 0 to 2 pi, there will be one value that works, because the 2 pi here is the same as the period. Think about that. We look for the solution between 0 and 2 pi. And the period is also 2 pi. So meaning that the solution will repeat for every 2 pi. So if we have a solution here, a period is 2 pi, so it will repeat after a 2 pi. So the solution will be here again. Or maybe go back to the other side, will be here. Either way, it is outside of 0 and 2 pi, right? Because the solutions are 2 pi apart. If you can only fit one of them in between 0 and 2 pi. If the solution we think smaller, then you can fit more than one. But because the period and the same as that interval, the same length, you cannot fit more than one solution between 0 and 2 pi. Because you cannot fit more than one solution between 0 and 2 pi, we can only choose one value for n. As soon as we find a value that works, that is our solution. Right, so it will be like that. So, I mean, it looks more complicated than it actually is, but we try to get the trig function by itself. Now, it depends on the trig function. If it is sine, we have the sine inverse and the supplement, and then we just do the math. In general, there will be 2n pi, because that is the period of sine. And now, if we want the solution in the specific window, then in this case, that window, the length is the same as the period. So we only have one value for n. And once we find the values that works, that will be our solution. Right. And let's look at this solution. this problem. So once again, we'll get the trig function by itself. So I will add square root of 2 to the other side. So I have 2 cosine of x equal to square root of 2. Now we divide by 2 on both sides. So cosine of x equal to square root of 2. Now, in this problem we have 0 to 360 degrees, so the answer is in degrees. Right, the answer in degrees. But regardless, the first thing we'll have is going to be the angle. In this case, x. The previous the angle is x minus pi over 4. So we just take whatever inside the trig function. Cosine inverse. If it is cosine, then we'll take cosine inverse. Now, the period for sine cosine, that is 2 pi or 360 degrees. So instead of plus 2n pi, I'm going to add n times 360 degrees. So that's one of them. Now, for cosine, not only we have that, what else do we have for cosine? For cosine, not only we have the cosine inverse, we will also have the opposite. That. Now, cosine inverse of square root of 2 over 2. (45 degrees) plus n times 360 degrees, or x equal to negative 45 degrees. So for cosine, we, along with the cosine inverse, we have the opposite to that. Right. Now, actually that is for x. Now, remember the answer have to be between 0 degree and 360 degree. Right. We'll choose some values for n. Now if n equal to 0, then we have 45 degree, which is good. 45 degree, and 45 degree is between 0 and 360 degrees, so that is good. Now, on this side, if we choose n equal to 0, we have negative 45 degree, and that is no good, because that's too small. Now, if it is negative or too small, we have to increase the number for n. Now, if n is equal to 1, we have negative 45 degrees. N is 1, so plus 360, that is 315 degrees. Now 315 degrees is between 0 and 360 degrees, so that certainly works. So we have solution of 45 degrees and 315 degrees. Remember, because the period for the problem is 360 degrees in our problem, which is the same as the length of the interval. So just like the last example, we can, if the interval of the solution is the same interval of the solution is the same as the period, we can only fit one of them in that interval. If it is smaller period, then we can fit more than one. But if it is the same length, we can only fit one of them. And so if one of them doesn't work, we just go until we find the n values that works in the equation. Now, once we find the n values that satisfy the condition between 0 and 360, in this case, we do not need to go any further. When we have a value that works, that would be it. That would be the solution. Now, find all the solution for cotangent equal to negative square root of 3. Now, of course, we can just use cotangent inverse. However, it would be better if we use the tangent inverse, because in the calculator or in the way we write the solution, we write the solution in sine, cosine, and tangent, the inverse of those functions. So it would be better if we write in terms of tangent. So cotangent is 1 over tangent. So that's the first thing we write. And this is negative square root of 3 still. Now, if we write that over 1, we can flip both sides. And we have negative 1 over square root of 3. Right? Now, for tangent inverse, what do we have? For tangent, what do we have? Of course, the first thing we do is always, if we have a trig function equal to something, then that something, then that angle or that argument of the trig function equal to tangent inverse of that. Remember, in tangent, the period is not 2 pi, the period is just a pi, so n times a period. Tangent inverse of negative 1 divided by square root of 3. We have negative 30 degrees. And then plus n times pi. Pi is equivalent to 180 degrees. Of course, we can just have that. Remember, in tangent, that's all we have. It's just the tangent inverse. There's nothing else. Just need to know that the period for tangent is a pi, not 2 pi. So that's all we do, really. In this case, there's no restriction in the solution. So that's what we have. Now, if we want the solution between 0 and 2 pi, different story. But of course, we can write the solution like this. Or we can say x equal to negative 30 degrees is negative pi over 6 plus n pi. So either that or that. Right? Yeah. So that's simple enough. For tangent, that's what we do. So it's a tangent inverse plus n pi. Now, if I change the problem here and say, find all the solution between 0 and pi, let's say, we just still want the solution for find x that is in uh, 0 to 2 pi. Now, suppose we solve this equation, but instead of all solution, we want the solution between 0 and 2 pi. So that's what we do. We choose some values for n, right? Now, when n equal to 0, put 0 in here, and we have x equal to negative pi over 6, because n is equal to 0. And that one is not between 0 and 2 pi. Now choose something else. How about n equal to 1? Because if it is too small, we have to choose bigger values, meaning that choose n to be bigger number. That gives us 5 pi over 6. And that's certainly between 0 and 2 pi. Now, do we have another one, or is that all we have? Now, think about this. We look for the answer between 0 and 2 pi. And in our problem, the period is n times pi. So we try to fit the solution that are about this much apart. One of the solutions we have is 5 pi over 6. And the solution will be this much apart. It will be 1 pi apart. So if we add a pi to it, it still is within the 0 and 2 pi. Because the period in the problem, the period in this problem is n pi, is pi, which is half the interval, half the length of the interval. So in that case, we can fit two of them in here. Right? I will write that in the next section. You will see. So in this case, if this is between 0 and 2 pi, we can choose two values. That gives us 11 pi over 6. So the reason we choose two values, because this interval, the length is equal to 2 pi. In our problem, the period is just a pi. The interval is long, the period is just half of that, so you can fit two of them in here. So in general, when we have the length and the period, we just divide the length by the period. The length is 2 pi, divided by the period of a pi, so that gives us 2, and this is two values for n. Right. Now let's go back to the previous example. In here we have the solution between 0 and 2 pi. The length here from 0 to 2 pi is 2 pi. The length of 2 pi. In our problem, we have plus 2n pi. Therefore, the period is also 2 pi. N times a period, so the period is 2 pi. Now, if we take the length of the interval divided by the period of our problem, 2 pi divided by 2 pi is 1. So that 1 is 1 values for n. So that's why in the solution we only have 1 values for n. Right? So once again, we will take the period, the length of the period, the length of the interval divided by the period. Whatever that number is, will give us how many values of n can we have. If it is from 0 to 2 pi, the length is 2 pi. The problem, the period is a pi. So we can have 2 values for n. So in this case, we have 2 values for n. That works. Right? So bottom line is, of course, it can be summarized into just this portion right here. Sine, cosine, tangent. The first thing, always take the inverse. For sine, along with the inverse, there's the supplement. For cosine, along with the cosine inverse, they're the opposite. For tangent, that's just the inverse. The only difference is, in the tangent, the period is a pi instead of 2 pi. Right. We will do more example of this, definitely. But now, we have to go to the equation in the more different forms. In different forms. Right. 2 sine square minus sine, 5 sine, let's do equal to 0. So first, just like every problem that we've done up to this point, try to get the trig function by itself. So now if we do the substitution, if we let u equal to sine theta, then the equation becomes 2u squared minus 5u plus 2 equal to 0. Right? So just let sine equal to u, and we have that equation returned to quadratic equation. This is quadratic equation, so I use quadratic formula. So negative b, just right, a is 2, b is negative 5, and c is 2. Right, negative 5 plus or minus negative 5 squared minus 4 a c over 2 a. Right, minus negative 5, that's a 5. Plus or minus 5 squared is 25, minus 4 times 8, 4 times 2 times 2, so 16. So we have 5 plus or minus square root of 9 is 3 divided by 4. So we have two solutions. One of them is 5 plus 3 divided by 4. 8 over 4 is 2. The other one is 5 minus 3 divided by 4 that is 1/2. So I have two solutions, u equal to 2 or u equal to 1/2. Right, so there are two solutions here. So I divide the solution in two columns. Right. So u is equal to 2 or u equal to 1/2. And u is equal to sine theta. So in this case we have two solutions. The first part is two equations. The first part is sine equal to 2. The other part is sine equal to 1/2. Because that's what u is equal to. Right, now just so for each one. For sine, the angle, the argument is going to be sine inverse. Plus 2n pi. Or we have the supplement to it. If I write like that, that may not be enough space. So either that, or we have theta equal to the supplement. The supplement is pi minus sine inverse of 2. Once again, plus 2n pi. Right. Sine inverse of 2, well, is undefined. Because of that, in this problem, there's no solution. The sine inverse, the domain has to be between -1 and 1. Right, so we have nothing here. Now go back to the 1/2. So sine equal to 1/2. The first thing always is the sine inverse. Might be plus 2n pi. Or the supplement to it. sine will have the inverse or the supplement. The period plus 2n pi. Now, so either that or sine inverse of 1/2 30 degrees, or pi over 3, pi over 6. Either pi over 6 or supplement to that. Supplement to pi over 6. And then we still have plus 2n pi. Pi minus pi over 6. So we have theta equal to pi over 6 plus 2n pi. Or over here, pi minus pi over 6 is 5 pi over 6 plus 2n pi. Now, the solution in our problem, we still want between 0 and 2 pi. So remember, solution have to be between 0 and 2 pi. So in that case, I will choose some value for n. Let's start with 0. If n equal to 0, theta equal to pi over 6, and pi over 6 is between 0 and 2 pi. So that works. But is that all we need? Is that all we have? So let's look at the problem. The solution between 0 and 2 pi, so the length from 0 to 2 pi is 2 pi. The period for our problem is 2n plus 2n pi, so the period is just a pi. The period is n times it is n times the period, so the period is 2 pi. So the length is 2 pi, the period is 2 pi. If we take the length divided by the period, two pi divided by 2 pi, the answer is 1. That is 1 values for n. So in our problem, there's only 1 values for n that will work, and when we find that is our solution. Next, if we choose n equal to 0 over here, we have the solution of 5 pi over 6, which is also between 0 and 2 pi. So once again, we find 1 value for n that works. That is the only solution that we have, because we only have 1 value for n that works for each case. Right, so of course we just have a trig function. Even though it looks a lot longer than it should be, because I write all the details. When we have sine equal to something, the first thing, of course, sine inverse, and then the supplement. And then we just choose how many values of n that will work. In this case, only 1 value for n that works. Once we find it, that's all we have. And make sure that, of course, sometimes we have no solution, because the domain of the inverse function, inverse of sine, cosine, have to be between -1 and 1. This is not, so no solution. Right. So that's what we have in our the solution we have in this problem is pi over 6 or 5 pi over 6. Right, now let's try order solution, order equation. 2 cosine square minus 3 cosine plus 1. This one we want all the solution. So in that case, we do not need to find the solution in a particular interval. Right, let's start. So first, let u be cosine. The reason we have to do that, because in this problem we have a square here, cosine of x. So we'll rewrite the equation in terms of u. 2u squared minus 3u plus 1 equal to 0. Right? Have to make that substitution. And then we can use quadratic formula. Right, b is -3, b squared minus 4ac over 2a. So that gives us 3 plus or minus 3 squared is 9 minus 8, which is 1. So we have 3 plus or minus square root of 1 is still 1 divided by 4. So in this case we have 3 plus 1 divided by 4. 4 over 4 is 1. And 3 minus 1 divided by 4 is 1/2. 2 divided by 4 is 1/2. So u is equal to 1, or u is equal to 1/2. Right. Once again we have 2. Two values for u, or 2 values for cosine, because u is equal to cosine. Now we have 2 equations. The first one is cosine equal to 1, and then we have cosine equal to 1/2. Now, as always, cosine or any trig function, we start with the inverse. And we can plus 2n pi. The cosine, not only we have that, we also have the opposite of that. Sine is supplement, cosine is opposite. And the period in our problem is 2n pi. It's 2 pi, sorry. So we'll do that. Same thing here, I can also write x equal to cosine inverse of 1/2. A period is 2 pi, so 2n pi. Or x equal to opposite cosine inverse plus 2n pi. Now, cosine inverse of 1. That is 0. Either that or opposite to it. Now that looks silly, but 0 degrees or 0 radian are the same thing though. Those two will be the same, right? 0 or negative 0 will be the same. So those together, we just have x equal to 0 plus 2n pi, or just 2n pi. Now problem we find all the solution. We don't have the interval in this case. So that's all we have, 2n pi. Now over here, we have cosine inverse of 1/2. (60°), which is pi over 3 plus 2n pi, or the opposite to that. That's all we have, because in this case we don't have any interval, any restricted interval. So we found all the solution, and those are all the solution to n pi, that and that. Right? If we have an interval, then we have to choose the length of that interval, divide by the period, and then we determine how many values of n do we have. We don't have that, so we don't need to do it. So that's all the solution we have. Right? I will not do this example. I just get you to start the problem. Now this equation, what happens if we have both sine and cosine though? Now if we have both sine and cosine, and first thing we do is try to get into either sine or cosine, because when we have both like this, it's not going to work. So what we do is we're going to square both sides. Square root of 3 square give us 3 cosine square. Now sine x plus 1 square. Sine x plus 1 square, sine x plus 1 times sine x plus 1. Multiply it out. Sine x times sine x, sine square plus sine x plus another sine x plus 1. So we have 3 cosine square equal to sine square plus 2 sine x plus 1. Actually, I think I need to finish this one. So just make sure that one very important thing here, because we square both sides. Every time we square both sides, we have to check with the original problem before we square it. I give you an example. 3 that is not equal to -3. This will be wrong. However, if we square it is right. It's true. Right? So just because the square works doesn't mean original problem without the square it will work. So that's why we have to check before we square. Make sure that's certainly true. Because when we square it's true, the original without the square might not be true. So that's why we need to check with the original equation. Right. So we square both sides. That's what we have. The next step is, it would be nice if we write everything in terms of just one variable, right? So, and we did this in the previous sections, previous chapter. More often than not, when we have cosine square, sine square, we use Pythagorean identity. The problem here is, which one do we use? Do we substitute for cosine square or we substitute for sine square? Now, of course, we have both cosine square or sine square, so we can use either one of them. However, because here we have the sine, so we want everything in terms of sine. So in that case, I will rewrite this cosine square is equal to 1 minus sine square. Right? I'll substitute that in here. 3 times 1 is 3 minus 3 sine square. Yeah, now we have everything in terms of sine. Make sure there's 3 when you multiply them out. Now move everything on one side. Keep everything on this side because that have sine, square, and sine. So minus 3 on both sides. And then plus 3 sine square on both sides. Plus 3 minus 3. So in this case we have 0, 4 sine square plus 2 sine minus 2. Was that equal to 0 already? So yeah, so that's equation. Now let's go back to what we did earlier. We can let u equal to sine x. So in that case we will have for u squared plus 2u minus 2 equal to 0. Quadratic equation, so I've used quadratic formula. Negative b, negative 2, plus or minus 2 square minus 4 a c over 2a. Negative 2 plus or minus 2 squared is 4. 4 times 4 is 16. And times negative 2 is 36 minus 36, so that's 36, and 4, that's 40. Wait a minute. $16, $32, $36, sorry. Yeah, there's 2 negative sign. Right. And then where we have negative 2, square of 36 is 6. So we have negative 2 plus 6 divided by 8. That is negative of, when we 4 over 8, so that just be 1/2. And then negative 2 minus 8 over 6 is minus 1. So we have 1/2 and negative 1. Right. Should have more space for that part. Right. So in this case, we continue. There are 2 values for u. So now we continue with 2 solution. First part, once again, there will be two solutions for u. So there will be 2 solutions for sine x. Sine x equal to negative 1. So for sine, it will have the sine inverse. Or the supplement to it. So sine inverse of -1 is -90 degrees or -pi/2. So if x equal to -pi/2 plus 2n pi or the supplement to it, pi minus that. So x equal to -pi/2 plus 2n pi. X equal to pi minus -pi/2 is 3pi/2 plus 2n pi. Right. Just one thing though. These two values, these 2 points actually identical because we talk about the unit circle. -pi/2 is here and 3pi/2 is also there. So these two corresponding to the same values. So because they are the same, we just say the solution for this part is let's use the 3pi/2 plus 2n pi. So we have one part here corresponding to the u equal to -1. Now the other part is u equal to 1/2 or sine x equal to 1/2. So we have x equal to the sine inverse or the supplement. So if x equal to sine inverse of 1/2, that's 30 degrees or pi/6. Or the supplement to that. So at pi/6 plus 2n pi or equal to 5pi/6 plus 2n pi. Right, so sine inverse and the supplement. Right, but that's not the end of it. Remember, every time we square both sides, we have to check the answer. So we do need to check the answer. The equation, original equation is square root of 3 cosine of x equal to sine x plus 1. Right. When we check, we just need one value for it. So let's choose n equal to 0. So we just check square root of 3pi/2 pi over 6 and 5 pi over 6. Let's check those values. Right. Now at x equal to 3 pi over 2. So we have square root of 3 times cosine of 3 pi over 2. Sine of 3 pi over 2 plus 1. Cosine 3 pi over 2 because it's this point. At this point, the x value is equal to 0, or the cosine value is equal to 0. Right? So I have square root of 3 times 0. Sine of square root of the sine of 3 pi over 2. The sine values of this point, the y values is equal to negative 1. So we have 0 equal to 1. Yes, that certainly works. So this is one of our solution. Now check for another one. I mean, 2 more, pi over 6. Square root of 3 cosine of pi over 6. Sine of pi over 6 plus 1. Cosine pi over 6 is square root of 3 over 2. So I have square root of 3 over 2. And sine of pi over 6 is 1/2. Multiply square root of 3 times square root of 3, so that's 3 over 2. 1/2 plus 1 is 3 over 2. So that. And at x equal to 5 pi over 6, square root of 3 cosine of 5 pi over 6, sine of 5 pi over 6 plus 1. Right, 5 pi over 6, that is in quadrant 2. And cosine of 5 pi over 6 will be similar to that, except it's going to be negative. And sine of 5 pi over 6 is positive. Right, so this side we have negative 3 over 2. This side we have 3 over 2. So as you see, if we square both sides, they will be equal. But if we don't square it, they are not. So this is not a solution. So we don't have that as the solution. That's what we have. Right, so don't lose. It's not that complicated. It's just a little bit long. From this equation where we have both sine and cosine, we have to square both sides to utilize Pythagorean identity. When we do that, when we square both sides, make sure we check the answer. Write the equation in terms of only one type of trig function, either sine or cosine. And then we solve for that. Give us both cases. And at the end, we need to check the answer. And in this case, only these two works. Only these two solutions work. Not that. Right, with that I finished section 6.2 here. As always, thank you for watching and see you in another video in trigonometry.